During a previous video, I turned this Arduino into a brick. No uploads, no communications, nothing. Today, we're going to find out what killed it and whether it can be brought back. At first, I thought I permanently broke this board. Before I relegate it to wall art, I wanted to answer what exactly counts as bricked. If the microcontroller is dead, this board is junk. But if we can still communicate with it, there is a chance we can recover it. First, I need to ask what the possible causes were. Let's go through and check each of these. Let's connect the board to the Pi I built last video and see if it can be reached. Nope, no dice, no serial output, no upload, nothing. Same failure as before. But this tells us something useful. The board's power is still intact. Previously, we were able to extract the firmware and bootloader fuses from the Arduino using my debugger, bypassing the USB. The flash memory responding to a read attempt is huge. If the flash was dead, we wouldn't get anything back. Further, the microcontroller itself must be alive. Upon closer inspection, we can see that these fuse values are set correctly. However, we did miss reading out the lock bit fuses. These fuses tell us whether or not we can read or write to the board. Next, let's check the contents of the bootloader itself. I don't know about you, but I cannot make heads or tails on what is happening here. But there is a bit of a clue here. This file ends relatively quickly. The Arduino has 32 kilobytes of flash memory, and we asked it to dump all 32 kilobytes. But something is wrong. This dump should be 32 kilobytes, but it ends here. Most of the address space is missing. This is not normal. I am going to hypothesize that the bootloader got corrupted. So how could our bootloader get corrupted in the first place? Well, when I was messing around with my AVR dude, there is a chance I told it to write my program file to the bootloader location in Flash. In effect, the program itself became the bootloader, which the Arduino absolutely cannot do anything with, effectively bricking the board from all future communications. Before we touch the bootloader, I need to do something very risky. If these fuse bits are wrong, the board may never accept a new bootloader. So, we're going to rewrite them, and hopefully not make things worse. Next, I am going to flash the board with a fresh bootloader. If my theory is correct, this should bring the board back. If I'm wrong, we're going to be back at square one. This is the most critical step here. And it took the flash. Now, let's try to upload something via USB cable instead of the debugger to confirm that it worked. Now for the moment of truth. Let's upload our blinking script from the last video. If it is able to upload and execute, we know the issue was with the bootloader. Upload complete. It's alive again. So, The board was never actually dead, it was just trapped behind a corrupted bootloader. This is further evident from the fact that our previously extracted flash memory is shorter than 32 kilobytes. Reading from the fixed board, we can see that we are now able to read the entire memory, all 32 kilobytes. This is what convinces me that the issue was indeed with my bootloader. Of course, if overwriting the bootloader still failed to bring my board back, my next step would have been to target the USB controller. It also has a set of debug pins, and the process to reset this component is similar to the microcontroller. Thankfully, I didn't have to go this route, because my debugger's header doesn't quite fit on this board without some additional wires. Now that I have returned this board to full service, I can use it for more security-related projects. Stick around for the next video, and we will resume building a secure system. Thank you.